Howdy, howdy. This is Mr. Potter. In today's lesson, we're going to talk about a couple of things here. The first thing I want to talk about is the difference between relative and absolute extrema. In other words, how we can tell empirically whether we're dealing with relative or absolute extrema. How can I tell just by looking at the function, not looking at the graph at all? And the second thing I want to talk about is the nature of the second derivative and how the second derivative is going to affect our graph in a similar way to how the first derivative has such a big impact on our graph. So I'm going to start with an example here. I'm going to start with y equals x to the 6 minus 6x to the 4th. And so the very first thing that I want to do, by the way, this is going to be on the restricted domain from -3 to 3, because remember that if I include boundary points and I'm dealing with a continuous differentiable function, then I have to reach my maximum and my minimum. That's what the extreme value theorem told us. So looking at this function on a restricted domain, on a closed interval, I want to start by looking at its derivative. So the derivative using the power rule, I get 6x to the 5th minus 24x cubed. And I know that extrema occur at critical points and boundary points. So I need to look at where my critical points are. My critical points are where my derivative is either equal to 0 or undefined. The undefined isn't really an issue here because we're dealing with a polynomial. But I can take this and I can factor a 6 out, and I can also factor out x cubed, and I'm left with the binomial x squared minus 4. And so I have three solutions to this. I have where x equals 0, x equals 2, and x equals -2. Now, some books will call these critical numbers or critical values, but what I'm looking for here is I'm looking for critical points. And as I mentioned before, a critical point is a point. So I'm dealing with the point 0, comma something. I'm dealing with the point 2, comma something. I'm dealing with the point -2, comma something. And to find out this y value, I need to substitute back into my original formula. So 0 to any power is 0, and when I subtract them, I end up with 0. 2 to the 4th is 16, and 16 times 6 is 96. If I take 2 to the 6th, that's going to be 64, and 64 minus 96 is negative 32. And because we're dealing with an even function, this y value is going to end up being the same thing. So I've got my 3 critical points, but I also have boundary points that I need to consider. And so I need to take a look at the restrictions my domain has been set up with. So I have a boundary point at negative 3, and I have a boundary point at positive 3. And so I'm going to need to evaluate this. And so when I take 3 to the 4th, I get 81. Negative 3 to the 4th is also 81. And when I take 81 times 6, I get 486. And when I take 3 to the 6, which is 729, and I subtract this 486, I end up with 243. I know, behold the power of calculators. And because this is an even function, again, I end up with 243. Now, a relative extrema has to occur at a critical point, which means when I'm looking for relative extrema, these are my only candidates here, just those on that line. But if I'm looking for an absolute extrema, now I can include these boundary points. And so my absolute extrema can include these points and these points. So I'm including all 5 of these points that I have listed. Now, for a relative extrema, I really do have to look at whether I'm increasing, whether I'm decreasing, when my derivative changes sign, because going from increasing to decreasing gives me a relative maximum. Going from decreasing to increasing gives me a relative minimum. Absolute is absolute. Absolute is which one is the highest. So of the 5 y values that I have, which ones are the highest? And looking at this, I have an absolute max, which occurs at the point 3, 243, and at the point negative 3, 243, because that's the largest y value that I reach. And the smallest y value has to occur at a critical point or a boundary point. So which one of these is the smallest y value? Negative 32 is my smallest y value. So I have an absolute minimum at the point 2, negative 32, and negative 2, negative 32. So now I want to consider these relative extrema. And if I want to look at relative extrema, I need to look at the behavior of my derivative function. So looking at the behavior of my derivative function, I don't want to I don't really care too much about this restricted domain anymore. I don't want to lock myself in to having to be between negative 3 and 3 when I'm talking about just when is my function increasing and when is my function decreasing. Although when I write my intervals, I'm going to have to include those as boundary points for my domain. What I notice is, of course, I've got critical points at negative 2, at 0, and at 2. Those are my critical values. So I need to take a look at the derivative at these four intervals that I've divided here. So I'm going to start by taking a look at any value that's less than negative 2. And again, remember, all I care about is the sign. So here, if I take a negative value in cubic, I'm going to get negative. But if I square a negative that's smaller than negative 2, I end up with the perfect square that's larger than 4. And so this ends up being positive. This product is negative, and a negative times a positive is negative. So on this interval, my derivative is less than 0, which means f is decreasing on the interval from negative 3 to negative 2. And again, remember this negative 3 comes from my artificial domain that I instituted here. For values between negative 2 and 0, I can go ahead and substitute 1, but I end up with a negative 1 times a negative 3, which ends up being positive. So my derivative is positive, which means that f is increasing on this negative 2 to 0 domain. A value between 0 and 2, I can try positive 1. So that's going to give me a positive 1 cubed, but this difference here is still a negative 3. And so a negative times a positive is negative. So f prime is less than 0, and so f is decreasing on this interval from 0 to positive 2. And for any value that's larger than 2, that value squared minus 4 will be positive. And if it's positive, then its cube is positive. And the product of two positives is positive. So my derivative is greater than 0, so that means that f is increasing on the interval from 2 to 3. And so what I've got here is I know that my function is increasing on several domains. It's increasing on the domain from -2 to 0, and on the domain from 2 to 3. And I know that I'm decreasing on the interval from -3 inclusive to -2 exclusive, and from 0 to 2. And if I'm looking for relative extrema, notice that I'm decreasing, then I'm increasing, then I'm decreasing, then I'm increasing. So that means something is happening here, here, and here. This, because I'm going from decreasing to increasing, this has to be a relative minimum. So I have relative minimums at the point -2, -2, -32. I'm going from increasing to decreasing, so this is a relative maximum. So I have a relative maximum at the point 0, 0. And then here I'm going from decreasing to increasing, so I have a relative minimum at -2, excuse me, at +2, -32. Now notice, I was able to find all of that information out just by looking at the nature of the derivative and the restrictions that I put on my domain. So all of this information, I can get a pretty good idea of what my graph is going to look like. I've got hard maximums at +3 and at -3. I've got absolute minimums. The lowest the graph can go at +2 and -2. So I can actually say that my range for this would go from a -32 to 243. I can make that call about my range because I know about my absolute extrema. And of course, the domain was given to me, this domain going from -3 to +3. But I don't know about the shape of what's going on. And to really understand the shape, I really need to talk about the nature of the second derivative. So, my second derivative, remember that when I talk about the second derivative, this is really the derivative of the first derivative, or the first derivative's slope. So when I talk about the second derivative being greater than 0, really means that f prime is increasing. And when I talk about the second derivative being less than 0, I'm talking about f prime decreasing on those domains. So what does it mean for f prime to be increasing? Well, what happens to f prime really depends on what f prime already is. If f prime is less than 0 and f double prime is greater than 0, that means my slopes are negative, but they're increasing. So that means that f is getting less steep. Because my slopes are already negative, but they're starting to become more positive. They're going towards the positive. So I'm going from a large negative number to a smaller negative number, and so my lines are getting less steep. But if my derivative was already positive and my second derivative was positive, that means my already positive slope lines are getting even larger, which means that f is getting more steep. In other words, I'm getting more towards a vertical curve than a horizontal curve. If I take a look at it from the situation where I'm looking at my second derivative being less than 0, if my first derivative was already negative and my second derivative is negative, that means I'm dealing with negative slopes, and they're getting smaller. They're getting more towards negative infinity. So my graph is getting more steep. But if I'm looking at f prime being less than 0, being greater than 0, and my second derivative being less than 0, I'm starting off with positive slopes, but they're getting smaller. So f is getting less steep. So what happens is that f prime tells me whether I'm increasing or decreasing, but the second derivative actually tells me about the shape of what's going on. So let me illustrate that in a table. So let's say that I'm dealing with the situation I know that f prime could either be positive or negative. And I know that my second derivative could be either positive or negative. Now, if my first derivative is positive, that means my function has to be increasing. No matter what, my function has to increase. The question is, how am I increasing? Well, if my function is already increasing, but the slopes are getting larger, that means that my line is getting steeper. And so that means I've really got this cup shape that's opening upwards. If, however, my slope was positive, but my slopes are getting smaller, that means that they're really getting less steep, and so I've got this shape which is opening downwards. So I can talk about the shape of my graph, not just whether or not I'm increasing or decreasing, but how my graph actually curves. And so concavity gives me this point. The second derivative really helps me illustrate that. Even if my first derivative was negative, which means my function is decreasing, there's two different ways that I could decrease. If my graphs are getting less steep because the slopes are negative, but they're getting bigger, that means my graph is tapering off, and so I've got this shape which is opening upwards. And if my derivative was negative, but my second derivative is negative as well, that means my slopes are getting more negative. They're getting more steeper. And so that means that my graph is actually curving this way. And so what I notice is that my second derivative is positive, means that my graphs tend to open upwards. So I'm going to be opening like this, or like this, or like this, or like this. And so we call this concave up, because each of these graphs appear to be opening in an upwards type direction. But if the second derivative is negative, then my graphs are going to look like this, or like this, or like this, or like this. And so we say that this is concave down. So I can tell by looking at the second derivative whether my graph is concave up or concave down. In other words, was my graph going to be curving upwards or curving downwards? And we get some really interesting things here. because in the situation where my, my graph is concave up and I reach a critical point, then that means something special. So if f double prime is greater than 0 at a critical point, then that critical point is a relative max. Excuse me, not max, min. If I'm concave upwards and I have a critical point, in other words, the tangent is 0, then that has to be a minimum in order to have this upwards curve. And similarly, if f double prime is less than 0 at a critical point, then that critical point is a relative maximum. Because if I've got a horizontal tangent and my graph is opening downwards, then it has to be a maximum. But if my second derivative is 0 or undefined at a critical point, then it is inconclusive. And I can see that happening here, because in both of these situations, I've got a critical point because my derivative happens to be undefined. But if my second derivative is 0 or undefined, I can't really tell the difference between having a maximum or a minimum. And so I really want to see a situation where at a critical point, my second derivative has a clear indication. Am I clearly larger than 0, or am I clearly smaller than 0? And this transition that we're talking about is called a point of inflection. So a point of inflection is a point where concavity changes sign. So I'm looking for a place where the concavity changes sign, either a place where the concavity goes from being concave down to concave up, or from concave up to concave down. And I notice that can happen in one of two ways. One way that it can happen is if I have the second derivative being 0. But another way that I can actually have that happen is if the second derivative is undefined. In other words, I almost have a vertical tangent there where my second derivative is undefined. So the thing is, I'm going to look for situations where my second derivative is either 0 or undefined. But just because my second derivative is 0 or undefined, that doesn't guarantee that I'm going to have a point of inflection. And I want to look at y equals x to the fourth, because this is a great example of how, even though we can use the first and second derivative to find extrema, we really can't tell that much about what's happening to the concavity of the shape. If I take a look at the first derivative, my first derivative is 4x cubed. My second derivative is 12x squared. And if I set that equal to 0, then I find out that x equals 0. So this is a possible point of inflection at x equals 0. But if I actually take a look at my concavity on this interval of 0, for values of x that are less than 0, this is positive. So my second derivative is positive. That means that f is concave up from negative infinity to 0. But if I try values of x that are greater than 0, I still end up with a positive function. So my second derivative is greater than 0, which means f is concave up from 0 to infinity. And I know that the graph of x to the fourth, a quartic graph, looks a lot like a flattened out parabola. It's much flatter at its vertex than a parabola is. Much flatter. It's actually like this. But I'm always concave up. I'm always opening upwards, even at this point where my second derivative is 0. So the thing is, just because the second derivative is equal to 0, that doesn't mean that we're going to have a point of inflection. Notice that I use the word possible point of inflection. And the second thing to remember is that a point of inflection is a point. So you need to give me an x and y coordinate. I need both of these pieces of information to actually have a point of inflection. So what I want to do is I want to go back to a familiar example. So the example we were talking about was y equals x to the 6 minus 6x to the 4th. And we noticed that this graph had an absolute maximum at negative 3, 243, and at positive 3, 243. These were our absolute maximums. We had absolute minimum at negative 2, negative 32, and at 2, negative 32. So I just want to keep this stuff in mind. We also had a relative max at 0, 0. So I want to keep this information in mind, but I want to take a look at it from the second derivative standpoint. So going to this, y prime would be 6x to the 5th minus 24x cubed. My second derivative ends up being 30x to the 4th minus 72x squared. Now remember, all I care about is the sign. So when I look at y double prime of negative 2, which was my first critical point that I came up with, at x equals negative 2, this is positive 16. And when I do 16 times 30, I get 480. 2 squared is 4, and 4 times 72 is 288. And what I end up with is a number that's positive. So if my second derivative is positive, this was our relative min. And remember that we did identify this as a relative min as well, both of these points. When I take a look at the second derivative at 0, now I'm looking at 0 minus 0, and this was one of our inconclusive cases. So this is one of those where I have to fall back to the nature of the first derivative. Am I increasing, then decreasing? And of course, if I look at y double prime at positive 2, that's still going to be the same number, 480 minus 288, which is still positive. So because our second derivative is greater than 0, this was a relative min. Now, concavity does not tell us anything about absolute extrema. It only tells us about relative extrema. The absolute extrema comes from our boundary restrictions. We have to look at each of our points and decide which one is the highest of the high and the lowest of the low. But the other thing I wanted to talk about is this idea of concavity. So if I were to take this 30x to the fourth minus 72x squared, this y double prime, and set it equal to 0, I'm going to have to do some factoring here. I'm going to factor out a 6x squared, and that's going to leave me with 5x squared minus 12. And so either x equals 0 or x equals plus or minus the square root of 12 fifths. Now I've done some calculations already. This is 1.549 for the AP. So these are possible point of inflection locations. So what I need to do is I need to take a look at this number line that we were just talking about and take a look at what's happening to my concavity at these places. So obviously something's happening at 0. Obviously something's happening at this positive 12 fifths root and at this negative 12 fifths root. And because this is negative 1.549, I know that negative 2 is on this side, which we've already found out that was greater than 0. So that means our F is concave up from negative 3, the restriction on our domain, to negative root 12 fifths. If I take a look at this, because this is 1.549, I know negative 1 falls in this region. So if I substitute a negative 1 in here, this is a positive value. But 5 minus 12 is negative. So my second derivative is less than 0. And so that means that F is concave down from negative root 12 fifths to 0. And so because my concavity changes, I know that negative 12 fifths root is at a point of inflection. So my point of inflection is going to be at negative root 12/5. And whatever I get when I substitute this in, this is one of those things where beautiful answers are wonderful. Negative root of 12/5 to the 6th minus 6 times negative root 12/5 to the 4th. So that's a beautiful answer. That's one of my points of inflection. If I continue looking at this, because this is 1.549, I know 1 lies in here, and again, substituting a 1 gives me that my second derivative is less than 0, because this is still a negative expression. So I am still concave down on this interval from negative to root 12/5, and so that means that this is not a point of inflection location, because the concavity doesn't change. I'm concave down, I'm still concave down. So looking at this positive 12/5 root, I know that 2 lies on this side of here, and we solved that 2 was greater than 0 as well. So because my second derivative is greater than 0, we know that our graph is concave up from root 12/5 to 3. And so I know that I have a point of inflection at this point. I know that my concavity changes here as well. So I know that I have a point of inflection at this point, this positive 12/5 root, which is positive 12/5 root to the 6th power minus 6 times the positive 12/5 to the 4th. But I know I don't have a point of inflection at x equals 0 because the concavity didn't change. I'm concave down on the interval from negative root 12/5 to 0, and from 0 to positive root 12/5. And I know that I'm concave up from closed bracket negative 3 to negative root 12/5. And from root 12/5 to positive 3. So I have a lot of knowledge about the situation of my graph here. Because of these intervals where I'm concave up, where I'm concave down, I can actually come up and say something about my graph here. I know that from negative 3 to negative 2, my graph was decreasing and concave up, which means my graph was decreasing and concave up. I know from negative 2 to negative root 12/5, I know that I was increasing and concave up. So my graph was increasing and concave up. From negative root 12/5 to 0, my graph was increasing and concave down. So I'm still increasing, but now my curve is kind of tapering off. At 0 to positive 12/5, I was decreasing and concave down. So now I'm decreasing and concave down. From root 12/5 to 2, I'm still decreasing, but now I'm concave up. And from 2 to 3, I was increasing and concave up. So now I'm increasing and concave up. And what this means is that my graph, I can get a pretty good gauge of what's going on here. I know that at negative 3, I was way up here at 243. And I know at positive 3, I reached that point again. I know that at negative 2, I'm down here at negative 32. As I am at positive 2. And I know at 0, 0, I'm at the origin. So I know from this point, I have to be decreasing and concave up. So I have to be decreasing and concave up. So I've got to be doing more like this. And of course, my drawing's not to scale. Gadzooks, that's the big eraser. And from negative 3 to negative 2, I'm concave down. From negative 2 to this negative 1.509, this negative root 12/5, have to be concave up, but increasing. But at this point, I change from being concave up to being concave down. And so my curve does this. And that's going to continue until I reach root 12 fifths positive. I'm going to be concave down and decreasing. Then I change from concave down to increasing from root 12 fifths to this 2. And then from 2 to 3, I'm increasing in concave up. So not only do I know I have this W-shaped graph, but I know how this graph twists and turns. This is something that the second derivative gives me. It allows me to determine when my graph is opening upwards versus when my graph is opening downwards. These points of inflection that I saw happening here at negative 12 fifths and again here at positive 12 fifths, those points of inflection are the places where my graph goes from holding water to pouring water. So I figure out a lot of information about my graphs. Now we're going to do a lot more practice in our day 2 lesson with this, but I wanted to go through this example. This is a fairly complicated example. Not all of the examples are going to be this complicated, but I wanted to make sure we understood the implications of what the second derivative changes does to the first derivative, does to the slope of the tangent line. So this is Mr. Potter. Thank you for watching. Have a great day.